In this question, we have 4 particles and it is a square of length 5 centimeters on each side. And let's look at the charges of these 4 charges. So Q1 is positive, so this is a positive charge. Q2 is negative. Q3 is positive, and then Q4 is negative. What is the magnitude of the net electric field to the particles produced at the square center? So the square center is somewhere right here, and we have to find the electric field. So when we have to find the electric field, the first thing we need to do is to put our measuring device. The measuring device is a positive test charge. So a little positive test charge right here. And then what I'm going to do is look at whether the positive test charge is attracting or repelling each of these charges. So let's look at Q1. Q1 is positive. Our positive test charge is positive. So our electric field here is, let's call it E1, is towards this side, so away from Q1. And for Q2, Q2 is negative, meaning it's an attraction. So I'm going to draw the arrow right here, and that is my E2. And note that I'm not drawing the arrows on the charges itself, not because it doesn't have an electric field, because that's not the question. The question is what is happening at the center. So I'm drawing all the arrows of electric fields at the center. Q3 is positive, so it's a repel again, so this way, and that would be E3. E4 is an attraction because Q4 is negative, so that would be on this side, and let's call it E4. So now let's look at each number or the magnitude. So E1 is KQ over R squared. So K times Q, so this is Q1, and Q1 is 10 nanocoulombs. So I'm just simply going to write 10 nanocoulombs for now, and divided by R squared. So this R is the distance between the positive test charge here, and Q1. And as you can see, it's the half of this diagonal of the square. So let's just call it R. For E2, we have K times Q is negative 20 nanocoulombs, and we are taking the absolute value. So we still write positive here, divide by R squared. It's the same R because it's also half of the diagonal. E3 is K times 20 nanocoulombs, divide by R squared. And then E4 is K times 10 nanocoulombs. Again, although Q4 is negative, we are taking the absolute value, divide by R squared. So let's just find the value of R. So R is the diagonal, divide by 2. So as you can see, this little triangle here, so Pythagorean theorem can be applied because it is a right angle triangle. So the diagonal would be a squared plus a squared square root, and then that is the diagonal, and then R is half of that. So we divide by 2, and that's the value of R. And if you plug in the values, you see that it is 3.53 centimeters. And we need to convert it into meters in our equation later. So let's just write 0.0353 meters. Okay, now we see that we have 4 vectors at the center of this square. So when we add vectors, they are in both 2D space. So what we need to do is to draw a chart. So this is the E field, and then let's look at the X and then the Y components of each one. So let's look at E1 first. So E1 is right here. So one thing to remember is to look at quadrants, and when we look at the quadrants, we are looking from the start of the arrow, not the quadrant that is given here for all of these charges, which is the first quadrant, but just look at where the arrows are originating from. So that's our XY axis right there. And then you can see now each of these electric field lines are in the 4 quadrants. So E1 is in the 4th quadrant. So E1 is in the 4th quadrant, meaning that the X component is positive, but the Y component is negative. So also, what is this angle right here? So this is a right angle triangle. So this angle right here is 45 degrees because it broke into 2. And 45 degrees is the angle for all of these. So this would be 45, this would be 45, etc. So going back to E1, we have positive E1. I'm just going to write E1 instead of writing what we found E1 up here at the top for simplicity. We have cosine of 45, and then Y is negative E1 sine of 45. And going down to E2, E2 is in the first quadrant, so both X and Y are positive. So we have positive E2 cosine of 45, positive E2 sine of 45. It is to note that sine 45 is equal to cosine 45. E3 is in the in the second quadrant. So we have X coordinate negative and then Y coordinate or Y component as positive. So we have negative E3, this is E3 cosine 45. We have positive E3 sine 45. Going down to E4. E4 is in the third quadrant. Both X and Y components are negative. So negative E4 cosine 45, negative E4 sine of 45. So here we have our X component. So this is the summation of all the X component. And then here we have summation of all the Y components of the electric field. Now because we have EX and EY, we want to find the net E. So let's just write each one separately. So we have EX. And as you can see, cosine 45 is common in all 4. So what I'm going to write is I'm going to take cosine 45 out, and then I'm going to write positive E1, positive E2, negative E3, and negative E4. And that is the X component. So now let's plug in our E values here. So I have cosine 45. Also, when we look at all the E values we found earlier, we can see that K is in the numerator of all of them. So is nanocoulomb, which is 10 to the negative 9. and then also r squared is in the denominator. So I'm going to factor them out. I'm going to have k r squared in the denominator, and then 10 to the negative 9, which is nano, and then I'm going to write what's left. So plus e1, so what's left is plus 10 plus 20, and then minus e3, so minus 20, and then minus 10. So what is 10 plus 20 minus 20 minus 10? That is 0. So we are multiplying 0 by everything, and that is 0. That is newtons per coulomb. Now let's do the y components. I'm going to factor out sine 45. What's left is negative e1, positive e2, positive e3, negative e4, then I'm going to factor out things again, factoring out k, r squared, and then 10 to the negative 9. So what is left? Negative e1, so we factor out k and r squared, so what we have is negative 10 plus 20 plus 20 minus 10. So we have 40 minus 10, so that's 20 within the brackets. And then plugging in our r value from here, you will see that it is 1.02 times 10 to the 4th newtons per coulomb. So the question is asking the magnitude. So we have an x component, we have an y component. So to find the magnitude of the net, we have ex squared plus ey squared, and then we take the square root. Since ex is 0, what we end up with is just the ey value.